Good evening, Kyle. We'll get started in about 5 minutes. Thanks for your patience. We'll get started in about 2 minutes. Thanks for your patience. All right, everybody. I think we'll go ahead and get started. Thanks for joining in this evening. For those of you that were here last week, I did post the recording from our last meeting. Well, I should say for those of you who weren't here last week, I did post a copy of our recording in the announcements so that if you missed us last week, you can go back and review that to look at the content that we covered. So what I'm going to do now is to go ahead and share my screen. So could somebody kindly unmute and let me know if you're seeing the course homepage right now?
Yes, ma'am.
Okay, thank you very much. I will also kind of give y'all a heads up. I'm having a little bit of connectivity trouble here this afternoon. My internet signal has been bouncing off and on. If that happens to me, please don't leave, because my experience is that it shortly restores itself, and I don't want you to think that I'm not trying to stay here with you. So seems to be technology issues have followed me since the storm, and I've been working to get it resolved, but today it seems like my connection wants to be temperamental. So we'll work through it and get through tonight's material. So I do want to just quickly flash the announcements before I jump in. So I did put out a project reminder, and we'll talk about this, you know, how you get started working on a project here shortly, but just to kind of, you know, keep you engaged with the project, I try to post periodic reminders regarding the project so that you don't forget you do have that on your plate. I posted an announcement earlier today as well, saying, you know, letting you know how you could join in this afternoon, and I'm glad that most of you found the link for tonight and joined in. And then notice that I did post the video from our class meeting on the 13th, as well as the link to the extra notes folder that I used regarding measurement. And then a link to the extra notes folder for every topic that we're going to cover this semester. You know, you have that link. No, I don't. Right. I needed to post that link for you last week. That's why I went. Oh, no, here it is. I posted this link some time ago, but just as a, you know, kind of reminder, I made it available when I posted the video from last Monday. And then for those of you who asked me, I did post a link to the full textbook. And finally, there is a link to a video dealing with the project that discusses all of the project. And so you have quite a few tools available in the announcement. So you want to check them frequently to see, you know, what is being communicated to you. So just a quick reminder about the syllabus. There are some of you who have not signed, dated, and emailed to me a copy of the last page of the syllabus. I haven't had a moment to reconcile who I have it from and who I don't, but I know I don't have it from everybody, because I would have more of them if everybody had sent it to me. So be sure to go back and do that for me, to send me a signed copy of the last page of the syllabus. And you can find that in the introductions weekly overview. There is just that page in a standalone format if you want that. All right. So any questions about anything so far that I've covered here so far tonight with you? All right. So last week we took a look at some generalities regarding science and how we do things in science, the experimental process, the scientific method. And then we jumped in to taking a look at a measurement. We looked at the base properties, the corresponding base units in the metric system, metric prefixes, and we ended by looking at unit conversions, how you do unit conversions utilizing what we call the dimensional analysis technique, which requires that you have a conversion factor. Now, last week I did promise you that I was going to end by looking at density, because it is an example of a derived property. And so I'm going to go quickly back into the notes that dealt with measurement from last week and take a peek at that, so that, you know, I'm thorough in what I'm sharing with you. Okay. So if you notice, I'm going into one of the links that's inside the extra notes folder from the announcement that I posted. So as I mentioned last week to you, and this can kind of serve as a review, there are 4 base properties that we deal with in this course: length, mass, time, and temperature. And there are 4 base or fundamental units that go along with those base properties. For length, we use the meter. For mass, we use the kilogram. For time, we use the second. And for temperature, we use Kelvin. But the other thing that we do in our quest to quantify our environment is that we make combinations of these base properties, and therefore combinations of the base units. So one property that we often measure is volume. And the way we get the property volume is to combine length times length times length. A lot of times in a math class, you might hear it referred to as length times width times height. But if you think carefully, width is a length and so is height. So what we're doing in essence is taking a length times a length times a length and getting this new derived property volume. When we do that, we have to make appropriate combinations of the units. And so we can take a length unit and multiply it times itself 3 times and get a volume unit. So we could take, for example, a meter times a meter times a meter and get meters cubed, and that would represent a volume unit, right? So we can take a length unit, multiply it times itself 3 times and get a volume unit. Centimeter times centimeter times centimeter gives us centimeters cubed, as you see on the screen. And we also see its equivalent in liquid units, right? Those of you who had me for lab on Wednesdays, we talked about the idea last week of liquid volume units, because you had to make measurement of volume, liquid volume units for canned items, right? And so we have a conversion factor given. If you recall last week, we talked about that. 1 centimeter cubed is equal to 1 milliliter. So we can take a length volume unit, centimeter cubed, and find its equivalent in a liquid volume unit, milliliters in this case. We could take a decimeter. A decimeter is a length unit. And if we multiply a decimeter times a decimeter times a decimeter, we get decimeters cubed, which is a volume length, a length volume unit, excuse me. And its equivalent in liquid units is a liter. So you have some examples of volume, which is a derived property, and appropriate volume units, which can either be length volume like centimeters cubed or liquid volume like milliliters. And of course, you know, in the English system, units like gallons, fluid ounces, pints, cups, quarts are also valid volume units. Now, below that, you see another derived property called density. And the way we get density is that we make a combination of mass, which is a fundamental property, divided by volume, which is a derived property. So you see, you can make all different kinds of combinations of base properties and a subsequent base units, or you can make combinations of derived properties. So when you make these combinations, you have to have appropriate derived or combined units. You see an example given there, grams per centimeter cubed. That is an appropriate density unit because you take a mass unit divided by a volume unit. So I could do, for example, kilograms per liter, because kilograms is a mass unit and liters is a volume unit. So a mass unit divided by a volume unit will give you a density unit, because to get the property density, you take mass divided by volume. And in the square on the left side, you see the formula for density. When you do formulas, you write that using the symbols. So the symbol for density is D, the symbol for mass is M, the symbol for V for volume is V. Okay. Now in the triangle, we have what I like to call my problem-solving pyramid. So let me see if I can open up. Bear with me for a second. I might have to stop share to do it because it's blocking my screen. So let me open a new tab, and I'm going to go to my whiteboard Fox. I like to use that tool I mentioned last week. And so I'll share this link with you when we're done. So as I mentioned, the formula for density uses the symbol notation D equals M over V. And I like to use, and we'll do quite frequently in this course, use what I call my problem-solving pyramid. Now, if we're looking at this screen right here, it's the pyramid with the smiley faces, but the symbols didn't come through the way that I wanted them to when I saved it as a PDF. It killed my symbols. So here is an example of the problem-solving pyramid. Now, why is this a useful tool? Because if you take the formula and put it in this problem-solving pyramid, you no longer have to worry about manipulating equation. Remember, I told you we use baby or introductory kind of algebra, very simple algebra. And in this case, I'm modeling that algebra with the problem-solving pyramid. So you don't have to use the equation. You can simply use multiplication and division. So for example, let me see, am I sharing? Oh, I do apologize. I am not. I'm just talking away and not showing you. I do apologize. So what I have here as a substitute for the pyramid that has the smiley faces in it is this pyramid that you see on the bottom here. Okay, so I took this formula and I put it in this pyramid so that I don't have to know how to do equations. All I need to know how to do is multiply or divide. And so, for example, let's say that I wanted to solve for density. Then I would simply cover up the D, and it tells me that to get D, I have to take M over V. What if I wanted to get mass, M? I simply cover up M, and it tells me to get M, I have to multiply D times V. And then finally, if I wanted to get V, I simply cover it up and I take M divided by D. So at every stage, whatever variable I'm solving for, I cover it up and then I simply multiply or divide depending upon whether the variables are right next to each other or one on top of the other. So if they're right next to each other, like D and V, it means I have to multiply. If they're one on top of the other, it means that I'm dividing, okay? So I will use this tool to make the algebra bearable in this class, simplify it so that if you're not overly familiar with how to solve equations, you can just simply use multiplication and division and accomplish what you need to. Okay, so let me stop share because it is blocking what I want to bring up here. All right, so now let me do. Bear with me. Let's see what's going on here. All right, yeah. It's kind of getting a little bit crazy here with all the screens open, so I apologize for that. All right, so now in this packet just below, you have some additional sample density problems, okay? And so each of these examples solves for a particular variable using the problem-solving pyramid, okay? And you might have seen some examples like this, or you will see some examples like this in problem set number 1. No, you did. It was due this past Saturday. So, and no worries, because I tried to be fairly lenient in scoring problem set number 1. So, if those examples were a bit challenging for you, you can come back and use these particular examples. There are 3 of them here, and each one solves for one of the variables in the density formula. So you can come back and try to use these as a guide. In addition, I am also going to be posting the solutions to problem set number 1. So you'll have those at your disposal as well, okay? So for these first couple of problem sets, I'm trying to be a little bit flexible and lenient because I know some people are doing the best that they can right now in terms of having access. Once we get past these first couple of weeks, then I'm gonna be a little bit more prescriptive and in terms of what I'm looking for when I score your items. And we'll talk about that later on, but I did want to bring to your attention the items that you had at your disposal in addition to what we covered and utilized last week, okay? So in the announcements, I mentioned to you, so wait, let me not go further. Let me just stop and ask real quick, are there any questions on that quick coverage regarding derived properties like volume and density? All right. So the other important thing that I mentioned to you that I wanted to talk about tonight was the project, okay? So now I think we should be good. I can kind of stay with this screen here. So I want to talk to you about the project. So the way I'm getting to the project, there are multiple ways, is that I simply clicked on assignments and activities on the left menu. Remember, to use the left menu, you have to be logged in through RPCC Canvas. If you're trying to use another school's Canvas login screen, it's not going to work. Okay. So once I clicked on assignments and activities, then I just clicked on project. Okay. And all of the information on the project is available to you here on this screen. Okay. What I'm going to do is to go into the project details, because that's where you find the description of what you need to do for the project. And that's why I said read it carefully, okay? And no worries, all of these other items we'll get to at some point along the way, because periodically I'll be talking about the project. But what I wanted to do now was, you know, give you enough information so that you could get started with the project. All right. So there are of course, with every assignment that you're doing here, there are goals, objectives that we're trying to meet with this project. And you know, one of the important things here is that you learn how to use library or internet resources to find this article. You need to be able to evaluate what you're finding to see if it's appropriate. You're going to summarize the article. You're going to relate it to what we've covered in class, and then you're going to be looking at APA format. Okay, so below the objectives for this is the directions. Okay, and so this is where I'm going to start explaining to you how you get started. All right, so a peer-reviewed research journal article is to be read and summarized in your own words. Okay. You must also clearly communicate how this article relates to what you have studied in lecture or lab, depending upon which class you're in. If you are in lecture and lab, you must do 2 different projects. So let's be very clear about that. Okay. So let me explain to you what this peer-reviewed research journal article is. So last week we talked about the scientific method, and we talked about the idea that there are scientists, some pure, some applied, who are actively doing research. When those scientists want to communicate what they're finding, what they're doing or working on, they write what's known as a research article. And those articles get published in research journals. But not just any research, any kind of publication, a peer-reviewed research journal, meaning it's open to be critiqued. It's open to critique by people who have expertise in that field. Okay, so a scientist who's doing research on astronomy might publish an article in the Journal of Astronomy. And that journal is available to, you know, anybody working in that area, as well as people at academic institutions like students, you, or faculty, me. Okay. And we can utilize that information to help us understand what new knowledge or new applications of knowledge are being generated regarding certain topics. Okay. And so your task is going to be to find one of those research articles, read it, and tell me what it's about in your own words. Okay. And then you're also going to tell me, how does that article relate to things you're studying in class, whether it's lecture or lab? And again, if you're in both classes, you're going to be doing 2 different projects. That is one of the reasons why I'm having you start early. Honestly, I would have liked if we could have started this about week 2, but the storm kind of, you know, pushed back our efforts to get started with the project. So we're, you know, you can consider that now is being formally assigned to you. Okay. And so what you're going to be looking for are articles, these research articles that are published in these research journals that relate to mechanics, which for us is motion, energy, waves, or thermodynamics. Okay, so one of those categories, oh, astronomy as well. I should add astronomy as a category. So let me do that real quick. I do apologize. That is definitely a valid topic area for you. Okay, I'll add it right here. Okay, so you can use articles that relate to any of those categories. All right. Now, those are very broad categories. So if you are looking for an article that deals with one of those broad categories, you're going to have to, kind of eliminate certain articles so that you get specifically an article related to the area that you're most interested in, for example. So if you're looking for astronomy articles, there are like millions of astronomy articles out there. You might want to pick one that you're interested in, for example, that deals with quasars. So you're going to refine your search as you go along. Okay. So how do you find these articles? Well, you can use the college's electronic databases. And the nice thing is that right from the left menu, there's a link to the RPCC library. Okay, so you could come into the Canvas course and click on the library's website right there. Okay, and then you can utilize the college's electronic databases. Okay, so let me see if I can open that for you. I'll open it in a new tab. Let's see, let me move this out the way and there. So you see the library's website, okay? And on that website, there's a good deal of information, okay? See, it says here, how to use library resources, okay? And so that's going to be your task. Your task is to figure out how to utilize the electronic databases that the library makes freely available to you, okay? All right. And so there's some specific information on utilizing the electronic databases, okay? Your job is to learn that process of using the college's electronic databases if you don't already know how. And the nice thing is from that website, you can reach out to a librarian and ask questions if you need to, and they can assist you. I will not assist you on learning how to use the electronic databases. That is part of this project for you to learn how. I just pointed you in the direction of them, so now you can go figure out how to use them, okay? You also have the, I give an important caution here. It says you might also find acceptable articles from scholarly journals online, but if you just go out and do a Google search, for example, when you try to access the actual article, they might ask you to pay for it. And I don't want you paying for things. If you use the college's databases, it's free. But if you go out and do your own web search, Google it, Bing it, or however you like to search for things, many times those articles aren't free. Okay, so what I always tell students, if you go out there and you pay $40 for an article and it turns out to be the wrong thing, you just lost your money, because I am not going to approve it, because I've given you access to free resources to find articles. The college electronic database is one of those sources, okay? Another source that I've made available is Hindawi. So Hindawi is what we call an open access journal. Okay, so basically all you find on Hindawi are peer-reviewed articles. You have to find one that's relevant for the project that relates to the topic areas. And the way you can use Hindawi is to simply click on that little search button in the upper right corner and then type in what it is you're searching for. Okay, just type in. So if I said media or wait, media, I think I just spelled that right. Okay, I just typed in meteorology. Okay, and you see there's 24 articles based on what on meteorology. And then I would have to dig into those articles to see if they met the requirements for the project. Okay, so Hindawi is another avenue for finding an article, and it's free because it's open. Okay, another avenue is an app that you can freely find in the Google Play Store or the iTunes Store. This app is called Arxiv, ARXIV. And so if you go to the iTunes Store or the Play Store and you do a search, this is the logo that you're looking for, okay? So I've given you 3 avenues for finding an article, okay? The college's electronic database, and it doesn't have to be just RPCC's library. You could use any college library. So if you have privileges at Southeastern, for example, you could use their library, okay? Just like you would have to figure out how to use RPCC's electronic databases, you would have to know how to use Southeastern's as well, okay? You could use Hindawi, and then you could use the Arxiv app, okay? So you're looking for a peer-reviewed research article on one of those 5 categories. I've given you 3 methods to find it. And the other important caveat is that the article, please listen to me, because I can't tell you how many times I get emails from students freaking out. It says clearly here, the article, not your summary. So the article that you have to read, not the summary that you have to write. The article must be at least 15 pages long, not counting the references. So let me give you an example of what I mean by that. So you see here on Hindawi, the nice thing is that I can download that PDF, okay? And if I scroll through that PDF, I can see this one's only 3 pages long. I can see that right here. But notice that it has references. Whatever page these references start on, well, put it this way. The references have to start on page 16 in order for the article to be long enough, okay? So that's why it says 15 pages long, not counting the references. So if the references start before page 16, I'm gonna tell you the article is not long enough, all right? You have until the 23rd of October to get your article approved. At 11:59 p.m. on the 24th, you can say, or at 11:59 p.m. on the 23rd, I'm gonna stop approving articles, okay? After that, any articles that I get, I'm gonna reject them, and you're on your own, okay? You can still do the project, but you're gonna be penalized if you don't get an article approved by that deadline, okay? So you're looking for a peer-reviewed research article on one of the 5 categories that I've listed. You have 3 free methods for finding that article. It has to be at least 15 pages long, not including the references. And you have until the 23rd of 11:59 p.m. on the 23rd of October to get it approved. What are your questions on how you get started with the project? Y'all still out there, huh?
Did you say how long the article we have to write must be?
You're not writing an article, you're reading an article. The summary that you have to write only has to be 2 pages long, but we're not ready to talk about that yet. I need you to get an article approved before we talk about what you actually have to write. So the first part of this is find an article, and then we'll talk about what you have to write at a later stage in the course. Anybody else, please ask your question. All right, so that part's out of the way now. We've got that taken care of. You can go ahead and get started with the project. And I would encourage you not to wait, because you're gonna find that these articles are, yeah, they're beasts, to say the least, okay? And if you have to do 2 of them, that's even more time consuming, so get started now, okay? If you are looking at the weekly overviews that I have here on the screen, you see that if we had started the course on time, we would already be in week 5, okay? And so this is the last week where you're gonna have to kind of like cram some things in for us to get caught up. And then after this week, you're gonna kind of move into a, you know, a bit of a slower pace schedule, all right? Let me just kind of give you some insight here as to where we're going. So tonight we're gonna move into our first, well, we're gonna start looking at motion, okay? And so first we're gonna look at objects that move in a simple fashion in 1 dimension. And then we're gonna move into talking about objects that move in a little bit more complicated fashion, 2 dimensions. But even that we're gonna see can be simplified, if you will. Now, you might notice there on the weekly overviews, if you're following me along on the screen, that the other topic area that's listed for this week is vectors. And so I'm going to kind of introduce some bits and pieces of vectors as I talk about 1D and 2D motion, but the vectors overview is something that you need to click on and work through on your own. The vectors overview is a self-guided overview, meaning you will cover it, okay? So there are some objectives here to guide you. There are a set of activities that you have to complete by this Saturday. And there are some resources that are available to you for you to complete those activities. But it is like you're gonna do this independently on your own. But I'm going to be touching on some aspects of vectors while I'm covering 1D motion and 2D motion tonight, okay? So that's where we're going, right? So let me click on the 1D motion overview, okay? So last week, we kind of got into this business of measurement, because as I mentioned last week, everything that we want to understand about our physical environment is based on measurement. And one very important thing that we want to be able to describe and discuss and analyze are those things in our physical environment that are moving. There are lots of things in our physical environment that are in motion. And so we need to understand how to describe quantitatively those things that are moving, okay? And so you can see some objectives here for understanding 1D motion. We're starting off with the simplest kind of motion. And so we need to understand, how do we know if something is in motion? What are the requirements to establish motion? We're going to look at some properties: position, speed, velocity, acceleration. We're going to look at distance. We're going to look at the relationship between position, velocity, acceleration. We're going to look at motion graphs. And then we'll look at how we perform certain calculations, right? You know, how we utilize some equations to help us calculate things for our moving objects. We'll look at particular type of motion called free fall. And then, of course, because you'll be completing a discussion, you're going to have to address certain questions regarding that topic, okay? So to help you meet those objectives, these are some activities that you have to complete. You have to complete a discussion that deals with 1D motion. You have to complete problem set number 2. Now, remember I mentioned last week that problem sets typically lag a week behind, right? So problem set number 2 actually deals with unit conversions, all right? And so you'll have an opportunity to practice unit conversions on problem set number 2, which is due by Saturday. And you see, you just simply click the link and you'll see some questions that you have to address. Let me remind you, when you are completing problem sets or answering discussion questions, solving problems, or whatever it is you're doing for me, you have to show your work. So when you address these 10 questions on problem set number 2, please show all work, okay? Otherwise, I'm not gonna give you credit for it, okay? All right. You also have a discussion that relates to 1D motion that you have to complete by this Saturday, all right? And the way the discussion works, remember, you post your answers and then you respond to 2 of your classmates. Some of you lost some points on the items that I scored earlier today because you did not respond to 2 of your classmates per the instructions that are provided with the discussion, okay? There's information on how to submit your problem set. And then if you're having questions, you can post a question regarding this assignment or anything regarding this course in the class questions forum, okay? And then finally, you have some resources and tools available to you to help with this topic area. I provided for you information from the textbook on chapter. Hi, everybody. Sorry about that. I'm back. Let me just go back into the share my screen again. I do apologize for that. All right, so here we are now. As I was saying, you have access to chapter 3 in the textbook, which you have to read. You have access to some videos that deal with 1D motion and free fall and motion graphs that you have to watch. We may take a sneak peek at the motion graphs videos here shortly. And then remember, I mentioned to you last week that the supplemental notes are my notes, okay? All right. So let me stop the share just for a minute. Yeah, it's still recording. I was just making sure that we're still recording so that I can share the recording with you, you know, once we're done. All right. All right, so let me jump into my notes. And remember, I mentioned to you, my notes always say supplemental. So last week I highlighted the how to study module for you. Hold on just a moment, please. Sorry, everybody, my cat decided to go berserk. All right, so I highlighted this last week and talked about it. And so as I mentioned, in every set of supplemental notes, you'll see this as a reminder on how you need to be preparing and moving through this course, okay? Here are the objectives for this material that I'm about to cover. And these objectives come right off of the objectives that are listed on Canvas. All right. So we have to get familiar with some terminology so that we can all talk about motion, you know, and be on the same page. One important vocabulary word that you're going to come across quite a bit in this course is kinematics. The word kinematics. So like a lot of things that we utilize to study physics, this term kinematics comes from the Greek word meaning motion. But what's important about this term is that we're looking at motion without considering its causes. So we don't care what made the object move or what caused the motion. We simply want to study certain properties about the motion. Okay. So when we study motion from a kinematics perspective, we don't worry about forces. Okay. Kinematics means that we're going to be looking at things like distance, displacement, speed, velocity, acceleration, time. Those properties of the moving object that we can determine and measure without worrying about what caused the object to move. Okay. And, you know, true enough, our world is 3D. But to keep things simple, we don't look at three-dimensional motion here. That would be like really complicated. But what we do focus on here is 1- and 2-dimensional motion. We're going to start off by looking at a 1-dimensional motion. And so, for example, we're looking at an object that was moving backwards and forwards, excuse me, backwards or forwards. That would be an example of 1D motion. Up or down, left or right, north or south. So we could use those examples of 1D motion because it's simple. It makes it much easier to analyze, okay? So there are some fundamental or basic properties that we look at when we're dealing with kinematics, as I mentioned. They mention a few here: position, displacement, time, velocity, acceleration. Okay. There are some others that are very close closely related to some of these properties. For example, distance and displacement are kind of closely related, but we'll look at what's the difference between the two. Speed and velocity are close to each other, but we'll look at what's the difference between the two. The other important thing in kinematics is that we want to study is how do these properties, how do these fundamental parameters that we can measure, how do they change? And so we have to understand notation to express the idea of something changing. And then we go back and borrow from the Greeks again. We borrow the Greek letter delta. Looks like a triangle. The delta symbol is what we use to indicate that one of those parameters is changing. So for example, if time is changing, or we want to look at how time is changing, we can represent that as delta t. So if we use the lowercase t to represent time, we can use delta t to represent a change in time, okay? And then in the back of your mind, you should always be thinking these things, because they're being measured, have to always have units with them. So for example, we could measure the change in time in terms of seconds, minutes, hours, days, so on and so forth, okay? The other thing that we need to have available to know that an object is in motion is to be able to locate an object, and then if we want to study its motion, we have to have a way of being able to specify that its location is changing. And so this idea of a reference frame is very important, okay? So we have to have a basis for describing or determining motion, and that basis allows us to locate the object, and that is a reference frame, okay? So we locate the object by providing its position. And position is a very easy concept to understand. That shouldn't be something that's totally foreign to you, because all we're saying is position is where the object is located within our reference frame, okay? And so when we specify a reference frame, we do it, we choose it in a way that's convenient for us, okay? And so they give you an example. It says, consider an airplane and its passengers. The location of the airplane at any moment is conveniently described in terms of its position relative to Earth. So in that respect, Earth is the reference frame. With respect to Earth, where is the airplane located? But when it comes to the passengers, the reference frame is more convenient if we choose the airplane, in particular the airplane's cabin, right? So for passengers, the airplane itself becomes the reference frame because we choose it in a way that is convenient and makes it easier to specify location. Let me give you a kind of an example to help you understand that even more. So I suspect that most of you are at home taking this course, or at a library, or at some location. And if I asked you, let's say, for example, if you're sitting at a desk or at a table, you know, following along, and I asked you the question, is your table moving? And so you could answer that a couple of ways, depending on the reference frame that we choose. If the earth is your reference frame, then no, your table, your desk, or your chair is not moving. But if your reference frame, for example, is the moon, if you're standing on the moon looking down at the table on planet Earth, you will see it moving. So it depends on what's your reference frame. Where are you measuring from? That's an easy way to think of a reference frame. So a reference frame is this fixed location that we utilize to establish motion. So we do that by measuring within our reference frame. Okay, that's why measurement is important. So they give you the example here, right, of choosing your reference frame for convenience. So once you have chosen your reference frame, you have a way to establish the object's position. If you then want to establish motion, you can say, how did the position of the object change in my reference frame? And when that object is changing its position, we call that displacement. So we measure how much the object's position has changed within our reference frame. We call that displacement. Okay? So there's a property that's very closely related to displacement, and that is called distance. And the distance, on the other hand, is just the length of the path that the object took to get from one position to another. So the length of the path that the object moves along as it moved from one position to another. Okay? So displacement looks at how the position changes. Distance just looks at what is the length of the path of our object as it moved. Okay? So they give you an example here. So we have a reference frame. Within our reference frame, we have home and a store. And we know the location or position of home, and we know the location or position of the store. Okay? And so, for example, if somebody moved from home to the store, we can look at how their position changed. We can also look at the distance that they covered. Okay? So let's imagine that a person walked from home to the store and then back home. So if we wanted to look at how the person's position changed from start to finish, well, they started at home, they ended at home. So the change in their position or the displacement is 0. However, in going from home to the store and back, they covered a distance of 6 kilometers, you see. So this establishes for you that distance, which looks simply at the path taken, the length of the path taken, can be very different from displacement, which looks at the difference between where an object stopped and where an object started. Okay? So, you know, you have to always be asking yourself when you're quantitatively describing or measuring distance or displacement, you have to be very clear about the definition and you have to be very clear about what it is you're asked to measure, right? Now we can see why sometimes students confuse distance and displacement, because, for example, if I went from home to the store and I stopped, I went in a straight line path from home to the store and I stopped. Then if I measured the distance traveled, it would be 3 kilometers. And also my displacement would have a size of 3 kilometers. But the difference is with displacement, I have to always specify a direction. So if I went from home to the store and I stopped, I would be 3 kilometers forward from where I started, or 3 kilometers east of where I started, or 3 kilometers in the positive direction compared to where I started. That is because displacement has to have a size, which is the number and the unit, and a direction, because it is a vector. Distance, on the other hand, only needs a number and a unit because it is a scalar. Okay? So when we deal with properties, we have to be mindful of how that property is defined, how do we actually measure it, and is that property a vector or a scalar? All properties that we deal with in physics fall into 2 camps. Either vectors that have to have a size, which is the number and the unit, and a direction, or scalars, which have a number and a unit only. Okay? So now, for example, if we wanted to quantify the object's displacement, what we're measuring is delta x. That delta, remember, says change, and we use the variable x to specify position. So to find delta x, we take the final position minus the starting position. Okay? That's how we would determine or quantify or measure displacement. Right? So in this equation, the initial position is given with the letter x and the subscript 0. You'll hear this referred to in textbooks or other sources as x naught. The 0 is sometimes referred to as naught. We use it x naught to specify the initial position. Okay, where did the object start from? And then x with the f as the subscript represents the final position. So the difference between where the object stopped and where the object started is the object's displacement. And when you find that, there's always a direction associated with that. And we'll look at that a little bit more carefully here in the next example and in the information below. It says, if an object moves from an initial position of 2 to a final position of 7 in a reference frame, then its displacement is 7 minus 2 or 5. For the reverse situation, where the object moves from a position 7 to a position of 2, its displacement is 2 minus 7 or minus 5. And this illustrates that displacement has both a magnitude and a direction. Okay? The magnitude in this case for either of those situations is 5, but the negative sign tells me direction. The negative sign on a displacement tells me direction. It tells me that I am 5 units to the left of where I started, or 5 units west of where I started, or 5 units in the negative x direction compared to where I started. So you can see the way we specify direction is using like a compass, north, south, east, west. We could use negative x or positive x, and we can use left and right. So positive value has positive x east or right associated with it, and negative 5 in this example has negative x, west, or left as ways of indicating the direction. But the magnitude in either instance is 5. And then remember, because we're measuring in the metric system, we use meters, or we can put a prefix on it as a way of specifying the unit, right? So we could say 5 kilometers. If the object moved from 2 to 7 in our reference frame, and you could think of this like a number line, right? From 2 to 7, then 5 meters east, 5 meters to the right, 5 meters in the plus X direction. If we're looking at the second scenario, we move from 7 to 2, okay? Then the final position is 2 minus the starting position, 7. So we get negative 5 meters. So 5 meters west, 5 meters in the negative X direction, 5 meters left, or we could simply write negative 5 meters. Those folk who understand vector notation understand the concept of displacement. When they see a negative sign, they know that's telling direction, okay? So here we are to summarize that, scalar and vector quantities. So a scalar is any quantity that we measure that has a magnitude. Magnitude means a number and a unit, but no direction, okay? It says there are many examples of scalar quantities, okay? And that, for example, time is a scalar. Why? Because you don't need direction to specify time. Speed. Speed just tells you how fast. It doesn't tell you the direction. Energy is another example of a scalar because it does not involve direction. Distance simply tells you how far along a path. You don't need direction. Simply a number and a unit. And temperature. Temperature doesn't have a direction, simply a number and a unit, okay? And so a vector is anything that we can measure, a quantity or property that we measure, and it has magnitude and direction. So a number, a unit, and a direction. So an example of a vector quantity is displacement. We saw that kind of worked out here a moment ago. We'll see velocity and acceleration are also vector properties, okay? We use arrows to indicate direction for a vector. And so scalars, because they do not have a direction, do not require arrows. And an arrow is great to indicate a vector because whichever direction the arrow points, that's the direction for our vector. And then we can make the arrow longer or shorter to indicate the size or magnitude of our vector, okay? So if we need a reference frame, many times what we do is we borrow from mathematics and we use a coordinate system to help us in indicating motion. And a coordinate system for one-dimensional motion is very simple because it can be forwards or backwards, left or right, up or down, okay? We can use a horizontal line to indicate that the object can move horizontally. And in that case, the right side is considered positive and the left side is considered negative. If our object can exhibit vertical motion, then we use a vertical line. And in this particular case, we say that up is positive and down is negative, okay? that's the way we're going to do it in our class because it's simple. You could use the reverse if you wanted, but we're going to stick to the convention that if we're doing horizontal motion, right is positive and left is negative. If we're dealing with vertical motion, up is positive and down is negative. All right. Time. Time is one of those important properties. And we know, as the saying goes, time waits for no man. So time is always moving forward, if you will, but not forward in the sense of a direction. Okay. We have to be very careful when we use everyday terminology that we don't confuse it with vector language, because time is a scalar and it does not have a direction. Okay. And so, there are different ways that we can measure time. You could use a watch, you could use a sundial, you could look at where the sun is in the sky. You could use a water clock, all kinds of different instruments that you can use to measure time. What we're most often interested in is how much time is elapsed. And so we find delta T. And that means we take the final time minus the starting time. So TF minus T naught. And as I indicated last week, the fundamental unit in the metric system for time is the second. Okay. And so a lot of times, to make things simpler, we will take the starting time as 0. Okay. So when the object first started its motion, the clock was set at 0, or T naught was 0. And so in that particular case, it becomes easy because delta T simply becomes T final, or T. Right? So see, what I'm covering with you now is convention and terminology, and how do you calculate certain properties? How do you measure certain properties? Because we want to give quantitative description. All right. 2 other important properties that we're interested in are average velocity and average speed. Okay. And so the way we define average velocity is defined as displacement, delta x, divided by delta t. Okay. And notice how they indicate the average speed, average velocity, excuse me. Notice is that script looking kind of a V with a bar on the top. Okay. And so average velocity is equal to displacement delta x over delta t. But if we take our starting time as 0, then we can just write delta x over t. Okay. And average velocity is a vector. Why? Because it depends on displacement, which is a vector. Okay. Average speed, on the other hand, is simply distance traveled divided by elapsed time. So the distance traveled just looks at how far the object moved over the time that it took. And that's a scalar. Why? Because distance is a scalar. Distance is a scalar, time is a scalar. When you divide 2 scalars, you get a scalar. Average velocity is a vector. Why? Because displacement is a vector. Time is a scalar, but when you divide a vector by a scalar, you get back a vector. Okay? And so you have to be very careful, because it depends on what you want to know. What are you measuring? Okay? Are you wanting to look at the difference between where the object stopped and where it started per unit time? Or you want to look at how far the object traveled per unit time? Okay? And you need to be mindful of the fact that the average speed is not necessarily equal to the magnitude of average velocity. For example, let's go back and look at our movement from home to the store. Okay? Let's say, for example, to go from home to the store and back, took 2 hours, okay? 2 hours. So they traveled a total of 6 kilometers in 2 hours. So that the distance traveled to go from home to the store and back is 6 kilometers. The time was 2 hours. So 6 kilometers per 2 hours or 3 kilometers per hour. But if we look at the average velocity, which uses displacement to go from home to the store and back, the displacement is 0. So then we have the displacement 0 divided by 2 hours or 0 kilometers per hour, okay? So you see the average velocity is 0 kilometers per hour, but the average speed is 2 kilometers per hour for the same motion, home to the store and back. So that's why they tell you that you need to be very careful with that, because the average speed is not necessarily equal to the magnitude of the average velocity. It depends on how the object is actually moving within our reference frame, okay? And so now be careful also, because the unit for expressing velocity is meters per second in the metric system, using our base units, right? And the unit for expressing speed is also meters per second. So if you try to use the unit as an indication of the property, that's not going to work, because you have a vector property velocity and a scalar property speed, both using the same units. So it is important that you know what property are you measuring, what is the definition of that property, and what are appropriate units for that property, okay? Instantaneous velocity and speed. So the previous definition focused on average velocity and average speed. This looks at instantaneous velocity and speed. So it says the instantaneous velocity, notice they don't use the bar over the variable. They just use the V here, right? You might be wondering, why do they use a V for speed, right? But a lot of books use S for distance. So be careful with that, okay? So the instantaneous velocity, this V of an object, is its velocity at a specific instant of time, okay? So average velocity looks at, you could think of it as the whole trip, whereas instantaneous velocity looks at a moment during the trip, okay? It is also a vector property, a vector quantity. So, you know, we're not going to get to calculating instantaneous velocity because it really requires calculus. That formal definition that they give means that we're shrinking the time interval down to an infinitesimal span of time. We don't use that. We don't have to calculate instantaneous velocity. Anytime you need instantaneous velocity, it will be provided. Okay, but remember, instantaneous velocity looks at your velocity at an instant in time, sort of like freeze frame. Okay, freeze frame. What's the velocity at that instant? Versus average velocity, which looks at the entire trip using the starting and ending points. Instantaneous speed is a scalar, and what you do to get instantaneous speed is you look at the size of the instantaneous velocity. Okay, so again, these instantaneous values we don't calculate at this point, they're provided. but I could give you the values. And if you don't understand conceptually what's the difference between the two, you could, have some trouble, okay? The other important property that we look at when we're dealing with kinematics, remember, we're looking at certain properties without respect to cause, okay? The other important property is acceleration. And the acceleration looks at the change in velocity over time. The change in velocity over time, okay? So this acceleration is definitely a vector because it relies on velocity. But when we think operationally, what are the ways an object can produce an acceleration? What are the ways an object can accelerate? How do we, look at the nuts and bolts of acceleration? Well, you could, because velocity has two features, speed and direction, then we can say that if we change the object's speed, the object is accelerating, or if we change the object's direction, it is accelerating, or we could change both, okay? So for an object to accelerate, you can change its speed, and we typically associate that with, accelerator, hit the accelerator, okay? Or the object can slow down, so hit the brakes. And then the other thing we can do to produce acceleration is change the direction, steer the wheel, right? So the object can speed up. That means its acceleration is going to be positive. And we typically think hit the gas. The object can slow down. That means its acceleration is going to be negative. We typically associate that with hit the brakes. The other thing is that we could change the direction by steering the wheel, or we could be doing both, changing the speed and the direction, okay? And we're going to keep our implementation of acceleration simple. Speed up, hit the gas, slow down, hit the brakes. Speed up, hit the gas, acceleration is positive. Slow down, hit the brakes, acceleration is negative. Or steer the wheel, or both, okay? Somewhere there, my definition for average and instantaneous acceleration didn't come through as clear, but no need to worry because we will not be calculating average acceleration or instantaneous acceleration. We will not, okay? You don't have to worry about average or instantaneous values for acceleration, and you'll see why in just a moment. But what you do need to understand is that in the metric system, using our base units, acceleration is expressed as meters per second squared. The unit for acceleration in the metric system, meters per second squared. Okay, so you can think of that as meters per second, right? So I'm gonna go to my whiteboard. See if I can scroll down, or no, I'll just open another one here. And I like to do this because I like to, for students to understand how you get the units meters per second squared, okay? So let me draw that for you. So acceleration, which is a vector, is found by taking here final velocity minus the starting velocity divided by the time. And that is because we're taking T naught equal 0, okay? And so you have to be thinking from the top of our formula, when we subtract the velocity, we get meters over seconds. And then on the bottom, because we're dealing with time, we have seconds. And this becomes meters per second times 1 over seconds. Well, where did I get that from? Because I can imagine writing this as a fraction. Okay, and then you can see very clearly this resolves itself to become meters times 1 gives us meter, and seconds times seconds gives us second squared. Oh, that's ugly. Let me write better square. Okay, so this is 1. I don't want you to mistake it for an L. Okay, all right. So that's how we get the unit meters per second squared for acceleration, because it looks at how the velocity changes per unit time, okay? And no worries, you won't ever have to calculate average or instantaneous acceleration, because that'll always, the value for acceleration will be either easily calculated or provided, okay? So here they talk about the idea of acceleration versus deceleration. Let me make this simple for you. We are not going to use the word deceleration. You are not allowed in this class to say the object decelerated. You can say the object had a positive acceleration or the object had a negative acceleration. If the acceleration is positive, we know the object is speeding up and the velocity is getting bigger. If the object is slowing down, the acceleration is negative and the velocity is getting smaller, okay? So we're not going to get into all the exotic combinations of acceleration in terms of how the velocity can change. We're going to keep it simple because this is an introductory level class, right? And another thing we're going to do to keep acceleration, our understanding of acceleration easy, is to only deal with objects that, or analyze the motion of objects that exhibit constant acceleration, okay? So we're not interested in looking at the average acceleration or the instantaneous acceleration, because we're interested in objects that maintain a constant acceleration, okay? And so, you know, we can model that in a great many types of motions, and simplify our ability to analyze, especially when we want to look at kinematic properties. To utilize constant acceleration is a much easier way to look at motion, okay? And so when we focus on objects that are moving with a constant acceleration, there are a set of equations that we can use all the time. And those equations relate to displacement, velocity, acceleration, and time. Those equations, those kinematic equations, become very simple to deal with. And so a common example is free fall. Okay, that is when we are looking at gravity or the gravitational acceleration being the driving factor of the motion. Okay, and so because we're looking at motion that is on planet Earth and gravity, which we'll be digging more in detail in later on in the course, but on planet Earth, gravity is constant, fairly constant, at 9.8 meters per second squared down. We can model what we call free fall utilizing the kinematic equations with constant acceleration, okay? And so these equations that I'm showing here on the screen are really useful when we're looking at motion that looking at an object that is moving horizontally with constant acceleration. Okay, so these are equations that we can use to analyze the motion when the object has constant acceleration. So the object is moving horizontally. How do I know it's moving horizontally? Because they're using X. We typically use X to signify horizontal motion. And notice in all of these equations, A is a constant. Okay? So our object is moving horizontally, left or right, east or west, negative X or positive X. We can use these equations to analyze that motion. These are called the one-dimensional equations for constant acceleration, the kinematic equations for constant acceleration. Okay? Now, I mentioned as an example, a real world example, of one-dimensional motion is free fall. Okay, so the question then becomes, what do the kinematic equations look like for an object that's free falling? Well, you see, falling is not horizontal. Falling is an example of vertical motion, and free falling is vertical motion that's being controlled by gravity only. Gravity only. And on Earth, that gravitational acceleration is denoted as G. Okay? And it has a value, a size of 9.8 meters per second squared. Okay? Now, the key thing about this free fall motion is there's no air resistance. Remember, I mentioned last week that sometimes in physics, we try to model things in the simplest fashion possible. It's not exactly real world because in the real world, there is air. But if we can ignore air resistance, or if the effects of air resistance are negligible, then we say we're in free fall and the object is being controlled by gravity only. The other thing you need to be mindful of when dealing with free fall is that the object can be free falling if one is simply dropped. If we drop it, then that's free fall. And that's the most obvious case. If we take an object to the top of a building and drop it and we ignore air resistance, free fall. That's fairly intuitive. But if we pitch the object down from the top of the building, because there is no air resistance. We're modeling it with no air resistance. So even if you pitch it down, it's still free fall. The difference in the case of pitching it down is that it starts with an initial velocity that is not zero. If we drop it, it starts with an initial velocity of 0. But if we pitch it, it starts with an initial velocity that's not zero, but the moment it leaves the hand, it's free falling. By the same token, if we throw the object up, once it leaves the hand, that is also free fall. That is also free fall. It's just that it has a starting velocity that's not zero. Okay? So drop the object, pitch it down, throw it up. Once it leaves the hand, if we're ignoring air resistance, that's free fall. Okay? Now, how do we use the kinematic equations that we saw for horizontal motion if we're going to use them for free fall? So what we do is we replace A with G, and we replace X with Y. So those equations become, oh, they didn't list them here. Okay, my bad. Let me do that for you. Okay, I'll go back to my whiteboard and we'll list. Okay. We'll list here. We'll put a box here, and inside the box, we're gonna do free fall. Ooh, that's ugly. I'm just gonna write like this. Free fall. Okay. I feel like I'm back in first grade again. All right. So the way this goes is that here we replace X with Y. So this becomes Y final equals to Y naught plus B naught T minus 1/2 G T squared. So you can see here, X goes to Y and A, and in the notes, they're simply talking about the size, but here I'm talking about the vector goes to minus G. Okay, all right. And also you have here, you have V final equals V initial minus GT. Okay, and then here, the last one, V final squared equals to V naught squared minus 2G, ooh, ugly, that's not good, 2G, oh, no way. Nobody will know what that is. 2G Y final minus Y initial. Okay? So this is what happens to the kinematic equations when we are dealing with free fall. This first one allows us to find position. The second one allows us to find the final velocity. And the last one allows us to find any one of these if we don't know the time. Notice this equation has time and this equation has time, but this last equation does not have time involved. right? So when we're dealing with free fall, we can take those kinematic equations and substitute y for x, and we can substitute minus g for a, okay? Blow this up again, all right? So the other important thing that we can do to analyze motion is that we can use graphs. We can use graphs to help us understand and analyze the motion of an object, okay? And so there are different types of graphs that we utilize to analyze motion, all right? We can look at displacement versus time. We can look at velocity versus time, okay? And we can also look at acceleration versus time, okay? So for this topic area, I have a nice video that I like to play. I'll play a portion of this video, not all of it, and then we'll move into looking at 2D motion, okay? Can somebody let me know, are you seeing that on the screen?
Yes, ma'am.
Okay, just wanted to make sure, because sometimes when I open all these different windows, the sharing doesn't work too well. So let me start it again. Oh, I wasn't trying to do that.
Dr. Zenon, we can't hear you.
Okay. Say that again for me, please.
Oh, we can hear you now.
I wasn't talking, the video was playing.
Oh, we can't hear the video then.
Wow, it's been playing for about 10 minutes now. I wish I had known that. Okay, so so you could see what he was doing, but you couldn't hear.
Yes, ma'am.
Okay. See. Bear with me for a second. Hmm. All right, so I do apologize. Then I'm gonna have to have you guys watch the video on your own, because if it's not sharing the audio with you, yeah, I don't have a way of, you know, playing the audio where you can hear it. I have watched videos over Zoom in various conferences, but I'm not sure about the audio. Okay, well, let me take this route then. Since you can't hear the audio on the motion graph videos, and I do apologize, but anytime you're seeing something on a screen like that and you're not able to hear whether it's me or the sound, please speak up right away so that I don't, you know, we're not losing time trying to you know, watch videos and we're not able to do it. I'm gonna have to figure that out. But what I can do is I'll go into the extra resources that I provided you. And if you go in on the 1D motion notes, okay, notice there are a nice set of notes on free fall here for you as well. But the other nice thing is that at the end of this packet, there is a whole set of example calculations. And there's a big part that talks about using motion graphs. Can y'all see that?
Yes, ma'am.
Okay. All right. So I'll kind of cover it myself here, and then you can watch the video on your own. So one of the types of graphs that he mentioned in the video was this idea of a distance versus time graph. Distance versus time graph, displacement versus time graph. As far as a graph is concerned, they're you know, they're pretty much the same thing. All right. And so when you're looking at a distance versus time graph, the slope of that graph tells you about the speed. Okay. And so if the line is steeper, that means you're going at a faster speed. Okay. And if the line is straight, that means that it's a constant speed. Okay. And then if the line is flat at any moment, then that means during that time when the line is flat, there is no motion. Okay. So we can see here, we got two objects moving, A and B. Object A is moving faster because the line is steeper. We can see, however, that you know, A also has a constant speed, whereas B doesn't, because B's line isn't always straight. But B does have a portion of time from 10 minutes to 20 minutes, for example, where the object wasn't moving, and that's because the line is flat. And this is only on a distance versus time graph, okay? So that's one type of graph. So you can see from these examples, we can use equations to talk about motion or to analyze motion, or we can use graphs. okay? Right? And so you can see here, for example, they tell you that you know, A had a steeper slope, so it was going faster. A also had a constant speed. Object B stopped moving between 10 and 20 minutes. But the other thing that we can use the graph for is we can find average speeds, because average only looks at what? Start and finish, right? So the finish position was 2,400 meters and the start was 0. So they covered 2,400 meters, and notice the time that elapsed was 30 minutes. So object A had an average speed of 80 meters per minute. B, on the other hand, only covered 1,200 meters, but it took the same 30 minutes. So its average speed is 40 meters per minute, okay? So you can use these graphs to determine certain information. And notice we didn't have to use any equations, okay? Here's another example of a distance versus time graph, but notice that this graph does not, it only has one object, first of all. And notice that there are no straight lines, no flat lines on this graph. It's only a curve, right? The line is curved. That tells us that the object accelerated, okay? Anytime we're looking at a distance versus time graph and the line is a curve, that means the object accelerated, okay? And we don't have to worry about finding the slope and all of that, because we're not gonna, that is akin to looking at instantaneous velocity, and we're not interested in that, okay? But, you know, just by the shape, we know the object accelerated. We can also look at a speed versus time graph. And notice on the speed versus time graph, the slope, the steepness tells us about acceleration. If the line is positive, meaning increasing left to right, the object is speeding up. If the line is decreasing left to right, we know the object had a negative acceleration and is slowing down. If the line is straight, the object had a constant acceleration. And if there's a flat line, there's no acceleration. So there's a constant velocity, right? So we can tell certain things about the motion just by looking at the graph, okay? So on this example, you see between 5 to 10 seconds, the object was slowing down. How do I know that? Because the line is decreasing left to right. When was the object speeding up? Between 0 and 3 seconds. Well, between 0 and 2 seconds, it had a different rate than 2 to 3 seconds, but it was still speeding up. And when was it moving at a constant speed? Between 3 and 5 seconds. How do I know that? Because the line is flat. And then what about when it was not moving? Well, for it to be not moving, the speed has to be 0. And so the speed here is 0 at the start and at the finish of 10 seconds, right? So you see, we can use motion graphs to describe our object, just as we can use equations to describe our object, okay? And again, I got to that by using the extra resources that are provided for you in the announcement, okay? So that was pretty much on 1D motion. 1D motion, we have some basic terminology that we need to understand, like what is distance, what is displacement, what is velocity, what is speed, what is acceleration. And then we have some equations that we focus on when the acceleration is constant, and that can be horizontal motion or free fall motion. And then we can use graphs to describe our moving object also, okay? Remember, the vectors portion of this, you're gonna cover on your own, but I have defined vectors for you, and I've given you some examples of vectors versus scalars, okay? All right, so now what I wanna do is I wanna go into the material that deals with 2D motion, okay? All right, we'll spend the remaining time looking at 2D motion. And so This takes us beyond looking at 1D motion, where we are looking at left or right, up or down, to looking at left and right. Okay, up and down. Okay, so we can combine that. Excuse me, I apologize, I said that wrong. So we can look at where our object is moving horizontally and vertically. Okay, so in 1D motion is horizontal or vertical, and 2D motion is horizontal and vertical. Okay, and you see the objectives here focus on the two types of objects that we're going to be studying: projectiles or objects moving in a circle. Okay, and so you have some activities that you have to do that relate to this topic. Problem set 4 actually deals with vectors. You won't actually complete a problem set on 2D motion until next week. Okay, all right. And you will have to complete the 2D motion discussion. So you do have several things that you have to get through this week that deal with 1D motion, vectors, and 2D motion, okay? And here you have 2 chapters in the textbook that I've made available to you, chapters 4 and 6. You have some videos that deal with 2D motion, as well as orbit motion and gravity, because we'll see that we'll see further down that this orbit motion is some pretty important type motion that we study. And so what I've made available to you are my notes that deal with projectiles and uniform circular motion. So I'm going to cover both of those. And then we'll look at some examples related to circular motion, okay? Let's hope this comes up pretty quick. There we go. Something's trying to come on. So again, we're moving into the world of two-dimensional kinematics. And the object that we want to focus on is a projectile. So what we're looking at when we're dealing with two-dimensional kinematics is that the object can move on a flat surface or plane, okay? So imagine like the object is confined to like a hockey rink, or and you know the objects can move on that floor, but not you know anywhere else. Okay, confined to that ice rink, for example, that's a flat surface. Or we could imagine a cannonball flying through the air and is relegated to like a vertical plane, okay? And so what we do when we study two-dimensional kinematics is we just take those one-dimensional kinematics variables and extend them to 2 dimensions. So instead of just having X, or Y, now we'll be using X and Y. So we need 2 parameters. Okay, so we now, what does our reference frame look like in 2 dimensions? As I mentioned, we need an XY pair. Okay, and a lot of times when we try to represent this on paper, if you've ever heard of the Cartesian coordinate system, the XY plane is used in math. That's what we use to model our 2-dimensional motion. Okay. So we have a horizontal axis and a vertical axis. So we need an XY pair to locate or analyze our moving object, okay? Now, the nice thing about this two-dimensional motion is that we can actually take the motion, the horizontal motion, and look at it separate from the vertical motion. Okay? Because even though we're doing two-dimensional motion where we have horizontal and vertical, the horizontal motion does not affect the vertical motion and vice versa. So what we can do then is take that motion and separate it. Look at the X motion by itself, look at the Y motion by itself. Hey, well, we know how to do that because we just finished looking at X motion by itself, Y motion by itself. So two-dimensional motion is just the independent cases of 1D motion happening at the same time. And that's what they're showing you in the picture here, okay? So it shows that you have two balls here being dropped. The red ball doesn't have any horizontal motion. The blue has horizontal and vertical motion, okay? Now you can see though, however, when you look at the vertical motion of the red ball and the blue ball, it's the same. How do I know? Look at the green vector arrows. The green vector arrows are the same at every instance that they're measured. So the vertical motion of the blue object is the same as the vertical motion of the red object, even though the blue object has horizontal motion as well. Why? Because the horizontal motion, the black arrows, does not affect at all the vertical motion, the green arrows. Okay. And so that's really nice that we can analyze those two motions that are happening simultaneously. We can analyze them independent of each other because we have a way to do that. We have a way to do that. And so the object that we're going to be using to look at this independent horizontal and vertical motion that's happening simultaneously is a projectile. And this projectile is moving in the air. It's only being influenced by gravity, no air resistance. It has a curved path and it has horizontal and vertical velocity. Now, the nice thing about a projectile's motion is that the horizontal velocity remains constant. So go back to your kinematic equations for horizontal motion and set the acceleration in the horizontal direction equal to 0. So Vx is constant. There is no horizontal acceleration, so Vx is constant. The vertical motion is controlled by gravity only. So go back to your free fall equations, and that describes the vertical motion. So you see here, they give you the equations for the vertical motion, okay? Because the object is in free fall. So the acceleration due to gravity, 9.8, they wrote 9.8 meters per second squared, okay? That's object is free falling vertically. And horizontally, there's no acceleration, so the velocity stays constant. All right. You don't have to worry about the maximum height and range of a projectile using these formulas because they rely on trig. The range formula for our projectile is simply found by using this formula. I'll see if I can write it here. I'll get a new whiteboard. And don't worry, I'm going to share links to all of these with you when I post the announcements. So So for our projectile, oh, okay, nope. So we got the horizontal motion. Okay, and that is the A equals 0. So VF equals V naught. And then you will have here X final. Oh, that's too big. X final equals V final. Well, let me undo that. So I should put here, to be consistent, X plus V naught T. Okay. But since the final velocity is equal to the starting velocity, you can, it doesn't matter which one of those you use. And typically we take the starting position to be 0, but that's easily, substituted. Most of the time the starting position is 0. So you wind up with X final equals V naught T, right? And this right here is known as the range. Okay, so most of the times we take this as 0. Okay, so that goes away. Okay, and now what about the vertical? Well, the vertical is simply free fall. Okay, so these same equations for free fall for a 1D motion apply to a projectile, which is 2D motion, right? So here you have this and this. Okay, so this is 2D. Right? So the nice thing is that when you want to analyze a projectile motion and you want to know something about the horizontal, use those equations on the left. When you want to know something about a projectile and you want to look at its vertical motion, use your free fall equations. But remember, these things are happening at the same time. Even though they're separate as far as analysis goes, they're actually happening at the same time. Okay, and so you don't need to worry about these equations here because they rely on trig formulas, and we don't do that in our class. So that's really all you need to know about a projectile, is that you're going to use your horizontal equations, which are greatly simplified because the acceleration is 0. And if you want to analyze vertical, use free fall. All right. And again, you have you'll have, I'll share these whiteboard screens with you when I do the post the videos and what have you for tonight's session. All right. So, and I do apologize that last week I was able to give you a nice little break, but because we had to get through the project and all of that, then I couldn't really spare the extra, if you will. Okay. So let's take a look at the other example of 2D motion that we deal with in this class, and that is uniform circular motion. Okay. So we're going to be looking at an object moving in a circle and its properties, and we can apply that to orbit motion, just like we can apply 2D motion principles to a projectile. We're going to look at principles that were of a circular motion and use it to explain orbit motion. Okay. So we're not worried about Newton's laws at this particular moment. What we are interested in is an object that's moving in a circle, and we want to take the simplest case of that, uniform circular motion. So this is an object moving in a circle with a constant speed. So now I want you to think back to our definition. Okay. This object is moving in a circle on cruise control, constant speed. But the one thing that is changing for this object is its direction. Its direction. Okay. So if this object is moving in a circle with constant speed, you're not hitting the brakes or the gas, but you are steering the wheel. And we said that if you do one of those, any one of those, then the object is accelerating. So because we are changing the direction, this object feels an acceleration. And we call that acceleration that the object feels when it's moving in a circle with a constant speed, we call that centripetal acceleration. Centripetal acceleration. Now we give that acceleration a subscript C to specify centripetal. Centripetal is a German word. It means center seeking. So this object is moving in a circle at a constant speed, but it's being accelerated toward the center of the circular path. Centripetal acceleration. Okay. And so there's some things that we can figure out for this object that's moving in a circle with constant speed. Okay. One is we can figure out what is that speed. To find the speed, you remember the definition of speed is distance over time. So for this object moving in a circle at any, when it makes a trip around the circle, it covers a circumference 2 pi r. And we give the time that it takes a special value, this capital T called the period. So to find the speed of our object at any given moment, 2 pi r over t. And its direction is always changing. Okay. We can also find the value of the centripetal acceleration by taking the speed, squaring it, and dividing by the radius. Okay. So I want you to imagine an object rotating in a circular path. Let me see if I can bring up a nice visual of that. I'll go under useful links to help me. And I'm going to bring up one of the simulators from Phsc because we use these a lot in lab. And in fact, we'll be looking at this exact same simulator in lab class on Wednesday for those of you who have me. So let's go find it. And that is, we'll get rid of all of these things. We don't need all of those. Okay. And we'll just focus on this guy, gravity and orbits right here, right? So the idea of circular motion, and we're going to use as our example this object that's orbiting. Okay. So we see here, can y'all see that screen? Okay. Somebody? Hello?
Yes, ma'am, we can see.
Okay, thank you very much, because I was starting to get worried. Okay, I'm going to switch to the Earth and a satellite because that happens to be one of my favorite types of scenarios. Okay, and I'm going to start it. Okay, so now you can see on this simulator, and I'll do it slow. Okay, this satellite is orbiting the Earth in a circular path. And it's exhibiting uniform circular motion because it's going around the circle with a constant speed. Okay. Notice the length of that green arrow is not changing, but the direction that it points is always changing. And because the direction is changing, the satellite is actually accelerated toward Earth. That blue arrow represents the acceleration. They call it the gravity force, but we're going to call it the centripetal acceleration. Okay. And notice it always points toward the center. Okay. So the object moves in a circular fashion with a constant speed, but it is constantly accelerated toward the center of the circular path. Well, a logical question to ask is, well, then how come the satellite just doesn't crash and burn into Earth if it's being accelerated toward the Earth? Okay. The answer is because of the high velocity, the green arrow. The high velocity that the satellite is maintaining helps to keep it in its circular orbit. It keeps it from spiraling down into the Earth. Okay. You could also look at it this way, that the blue arrow, which represents the centripetal acceleration, which is being provided by gravity in this instant, is what keeps the satellite from going off into space at a tangent to a circular path. So for example, if I turn gravity off, I had that switch, you see, the object goes off in a straight line at a tangent to the circular path, wherever it's at the moment that that centripetal acceleration, which is being provided by gravity, is cut off. Okay, so the forward velocity keeps it in its, counteracts the pull of gravity, so it doesn't go in, spiral into the center of the Earth, and the pull of gravity keeps it from going off in a straight line into outer space. So they kind of work to counteract each other. Okay, so that's a visual of uniform circular motion. Okay, and those of you who have me for lab, you're going to get to actually play around with that in a bit more detail. Okay, but we can find the values and the sizes of that speed and acceleration using these formulas. Okay, we're not interested in the force, the centripetal force at this point. We'll get there later on. We're just interested in the speed and the centripetal acceleration values. Okay, and they show you here, it's not a nice drawing. That's why I brought up the simulator. The idea that the centripetal acceleration always points inward toward the center of the circular path. And so that's pretty much what I wanted to cover with you there. Okay. Now, in your extra notes folder. So I'm going to go back into those extra notes. See, this is a great resource for you, these extra notes. And let me go in. There's a folder with 2D motion. See, there's a folder for every topic we cover. There's one on 1D motion. There's one on 2D motion. And in this 2D motion folder, there is an example, which goes faster, a GEO or a LEO. Okay. So a GEO is a geosynchronous orbit satellite. A LEO is a low Earth orbit satellite. And your International Space Station, if you're not familiar with that, the International Space Station is a low Earth orbit satellite that is, orbiting the Earth, and there are people, scientists, otherwise living on it. And they are doing all kind of neat scientific experiments to see, help us answer the question, what is it going to take for us to permanently live somewhere else besides the Earth? A geosynchronous satellite is like your communication satellites, like Verizon, Sprint, or spy satellites. And all of those, there are hundreds of them out there orbiting the Earth. And so I wanted to use our understanding of uniform circular motion to answer the question, which goes faster, a GEO or a LEO? Okay. So a GEO is a satellite that rotates around the Earth once every day. And we know this means that it has a period, big T. Big T is the time that it takes to go around once. Because it goes around once every day, that period is 24 hours. And we also need to know how far is it from the center of the Earth, because we measure the radius from the center of the circular path. Well, we know that these satellites are about 22,000 miles above the Earth's surface, or about 26,000 miles from the center of the Earth. And we want to know, what is the speed? How fast is it going? It's uniform, the speed doesn't change, but how fast is it? And then how much acceleration toward the center of the Earth? So we have the period and the radius. Speed, if you recall, is distance divided by time. So the distance is the circumference, 2 pi r, and the time is the period, capital T. And so we do 2 pi r, where r is 26,000 and T is 24 hours. And I did it in miles per hour, so you would have, you could kind of relate it to something, right? You've driven in a car, been in a car that goes miles per hour, so we can use that as a kind of a guide, if you will. So when you do 2 times pi times r divided by T, you get 6,803, and I round it off because this is just an approximation. So roughly about 6,800 miles per hour, 6,800 miles per hour, which is pretty fast. 6,800 miles every hour. So, I mean, even the fastest jets go about, they can go about 500 miles per hour. This one's going 6,800 miles per hour. How much acceleration? Well, you would imagine that it has to have a nice size acceleration to maintain, to counteract that high tangential speed, or what? It'll just go off in a straight line, right? So we take that speed and square it and divide by the orbit radius. So that's 6,803 miles per hour. We have to square it. We have to square the number and the unit, and then divide by the radius, 26,000 miles. When you do that math, that comes out to be 1,780 miles per hour squared. Okay. So you see, we can use those two formulas to figure out what's that speed that this satellite is going to maintain, and how much is it going to be accelerated toward the center of the Earth. Let's take a look at our LEO. right? So this LEO is a low Earth orbit satellite like the International Space Station. And it makes a trip every 90 minutes or an hour and a half, 1.5 hours. And these low Earth orbit satellites are at about a distance of 100 miles away from the Earth's surface. That's why if you have a nice clear sky and the International Space Station is passing overhead, you can actually see it. This is only about 100 miles or so above the Earth's surface. That's about 4,060 miles from the center of the Earth. Remember, the orbit radius, you measure not from the surface, but from the center, okay? So then let's see, how fast is it going? What's its speed and how much centripetal acceleration? So go back to our formulas. Speed is distance over time. So we do 2 pi r over t, right? Distance is the circumference. Time is the period, capital T. So 2 pi r over t. So 2 times pi times 4,060, and I approximated that orbit radius. And the time is about 1.5 hours. So that gives you 16,998 miles per hour. So that's a 17,000 miles per hour. So the International Space Station is in orbit around the Earth, and its speed is about 17,000 miles every hour. So that's a tremendous speed compared to the GEO, right? Well, if it has that huge a speed, it must have a really huge acceleration. So let's take that speed, the number in the unit, square it, and divide by the orbit radius. So that's 16,998 miles per hour squared, divided by 4,060 miles. That gives us a centripetal acceleration of 71,166 miles per hour squared. So it's going really fast, and so it's being pulled into the center of the Earth with a much larger acceleration. But remember, those two, the speed and the acceleration, are kind of counteracting one another, right? Okay, so that the International Space Station doesn't come crashing into planet Earth, right? So that's an example of utilizing our uniform circular motion formulas to look at a real scenario of these different types of satellites. Okay, so that is pretty much what I wanted to cover with you. So what I'll do now is stop share and ask, what are your questions of me regarding what I've covered tonight, or the physical science, the project, anything you might want to ask before we stop for tonight, cut off the recording, and do it all over again next week, right? What are your questions? Yeah. And I do apologize that I couldn't get the audio to work with the motion graphs. I'll work on that. Maybe next week we'll just, if I can figure it out, we'll take a quick peek as kind of a review. All right. Well, hopefully that means that you're all good, but it goes without saying, if you're having any difficulties between now and next week, you have questions, please reach out to me. You can email me, you can you can come during office hours, whatever you need to do, please don't hesitate to reach out to me. Thank you for joining me tonight. I'll post this video as soon as I get it captioned, along with the links to our whiteboards. Everybody have a good week. Lathan, Stephen, and whoever's student, we're done for tonight.